All right, guys, so what I'd like to do now is introduce you to something called Kirchhoff's laws or Kirchhoff's rules. All right, this is actually one of my favorite parts of circuits just because I think it's so neat the way it works. Now, the principles here are pretty straightforward. They're things actually that we already know, okay? The first of Kirchhoff's laws is that the sum of the currents at any junction is zero. All right, so what does that mean? That just means that if I have two currents coming in, I1 and I2, that has to equal the amount of current going out in I3. In other words, that I1 plus I2 equals I3. Right? And that should make sense because the current is the number of electrons per second that are going through a specific wire. So if you put two of them together, you should be able to just add up the number of electrons to get the new current. All right. Now, this will work. One of the neat things is that this will work even if you don't know which direction the current is going. All right. Look at my drawing over here on the left-hand side. I've got a couple of batteries here. This gets kind of confusing when we have a couple of batteries, which is why we're going to lean into Kirchhoff's laws. Now, it's really difficult to know right off the bat which direction all the currents are going. And you may not know. But the neat thing is you can make that choice. And as you work through the problem, if you solve and you get a negative value for current, it just means that the current should have been going the other direction. You chose the wrong direction. No problem. Now, what I'll usually do is I'll look at my batteries, all right? Like this battery up here at the top, this guy right here. Obviously, I've got the positive side here and the negative side there. So chances are current's probably going this way, right? And it's going into it like that. So if I look at this junction right here, that right there, I'm going to call that current 1. I'm going to say that current is going to be coming into that junction, right? I might do the same thing with my 9-volt down here, right? If I look at the 9-volt battery down here at the bottom, I'd say, oh yeah, that looks like positive and negative. Well, so I'm probably going to say that current, I'm going to call that current 2 because the first one was current 1. I'm going to say the current probably goes this way, right? From the positive towards the negative. Now, as long as it's a single stretch of wire, the current should all be the same there, right? We talked about this in class, that the current all through here should be the same because there's only one wire. There's nowhere where it splits. It doesn't matter if it goes through a battery resistor. It's all going to be the same current. Same thing down here. When we look at all this is all going to be one current. Now, the current at the bottom and the current at the top, I1 and I2, those don't have to be the same because there's a junction somewhere in the middle. And so current could be added in or taken out at that point. Now, of course, we do have this section here in the middle. That is going to be my current 3. Now, based off of what I see here, I see both 2 and 1 going into this junction here. And so I'm just going to say, well, I think I3 is going out. Now, all of that is complete guesswork, and that's fine. That's not a problem here. Like I said, if you made a mistake in the direction, it'll just come out as negative later, and you'll be able to solve it. Okay? But these directions are important, so you should always determine the directions before you do anything else. But I can now use this Kirchhoff's first law and say at the junction that I'm talking about, right, this red dot that I made, I've got I1 going in, I've got I2 going in, and that should equal then the only one going out, which is I3. So I have this equation right here. Now that's all nice and good, but it does have 3 variables in it. So not super helpful yet. Now, if there are other junctions, I will use the other junctions as well. Unfortunately, this one over here just has 3 going in and then 1 and 2 going out, which would be exactly the same as the one that I just wrote. So I'm not going to write a second one here, but if I had other junctions that would lead to different equations, I could use more than one current equation. It's a little bit easier to work with, okay? Now we're going to go on to Kirchhoff's second law. Now, Kirchhoff's second law says that the sum of voltage changes around a loop is equal to 0. And it's usually shown like this. The sum of the voltages around a loop equals 0. Now, of course, the question is, what do you mean loop meant about on a loop? What's you talking about? All right, well, all I'm talking about is pick a point, anywhere on the diagram. So I'm going to choose this point right here. So I'm going to start at that point, and then I'm going to go in a loop. Now, you can choose any loop, but you do have to go all the way through and return back to where you came from. That is a complete loop. Now, what we're going to do is as we go through that loop, we're going to look at each of the resistors, each of the batteries, and we're going to determine what that component is doing to my potential. For example, I'm starting at the green dot here. So the first thing I'm going to do is I'm going to go to the left. Now, you could have gone to the right. It doesn't matter. Okay, I'll show you one later that we go kind of the opposite direction. It really doesn't matter. I'm going to go to the left here, and I'm going to go through that 6-volt battery. Now, as I go through that 6-volt battery, I'm going from the negative side to the positive side, so that means I'm going to gain 6 volts. All right. Now, I'm going to keep going around the loop. And as I go around the loop, I'm going to go around the bend. I'm going to go down the left side. Nothing's happening. Now, as I go through the bottom part of the loop, I'm going through this 2-ohm resistor. Now, we know that I equals delta V over R, right? Which also, you can just rearrange that. Delta V equals IR. And so what's happening in that resistor is I'm losing some potential due to the current and the resistance. Now, I'm losing because I'm following the direction of my current. That's important. This is why it's important that you label the directions of the currents. So I'm going through the direction of the current there, and I'm going through that 2-ohm resistor. So as I go through that 2-ohm resistor, I'm going to be losing potential. So I'm going to put a minus, and then I have the current, that current, which is I3, which is multiplied by the resistance of that resistor, which is 2 ohms. And I'm going to get rid of that V right there just because we know they're all in volts. So we've got the plus 6 from the battery, the minus 2 I3 because it's going through that resistor. And then the current is going to go, following my loop still, I'm going to go up through that 1 ohm resistor. So again, look, the direction of the current is going upwards there. I'm looking at the direction that I defined earlier. So if I go that direction through the resistor, then I'm going to lose some potential again. So I'm going to go minus 1 ohm times the current, which that is current number 1. Now, Kirchhoff's second law says that if I go all the way around the loop, that total change in potential should be 0. Now, this should kind of make sense because what we're talking about here is we're starting at one location on the wire and we're just going all the way around that wire back to the same location. So it should have the same potential as that location, right? And so since there's no change in potential, then we have to have lost and gained the same amount of potential as we go through that full loop. So we have a second equation. Note that I now have 2 equations and I used the same variables. The variables were the currents. Now, it's possible that they give you the currents and the unknowns are the resistors, and that's fine as well. But in this case, we have all 3 currents being unknown. Now, at this point, we are going to have to do one more equation because I do have 3 unknowns. And so I'm going to need to do one more loop. So this time you can do the bottom loop down here if you want. You could go through that bottom loop. I'm going to do something a little bit different just because I want to show that we can. And so I'm going to go through the big loop. I'm going to start at this 6 volt and I'm going to go all the way around the outside like this and then back to the 6 volt again. Okay, just because I want you to see what happens as we hit some different things. All right, so I'm actually going to start at the same place right here. And then I'm going to move through that loop. So I'm going to go across that 6 volt battery. Now again, I'm going from the negative to the positive, so that's going to be a plus 6 there. And then I'm going to go down, 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 and I'm going through. I haven't hit any resistors yet, but now I'm going to hit this 3 ohm resistor. Now this is a little bit different because notice that I said the current here was going to the left, which means that the right-hand side should be the bigger piece, and then it should have lost resistance as it went to the left. If I'm going the other direction across the resistor, according to my loop, that means I should actually go up in potential as I go to that other side. And so what I want to do is I'm going to now add in the 3 ohms times the current there, which is current 2. Okay, now remember, if I go in the direction of the current, I should be losing potential because I lose potential as I go through that resistor. But if I go through a resistor in the wrong direction, remember, it's not the current that's going the wrong way, it's me going from one side of the resistor to the other. I should go up in potential. All right, so now I'm to the other side of the resistor. I added that 3i2, and now I'm crossing the 9-volt battery. But notice that I went from the positive side to the negative side. So what that means is that I should drop 9 volts of potential as I go from that positive side to the negative side. And then we go on, we go through here, we go back up, we hit that 1 ohm resistor. I am going in the direction that I labeled for that current 1 there, so I'm going up through that. So I'm going to go minus 1i1, and that, when we put it all together, again, we're going to arrive back at the place we started from, and so that total should be 0. So what I have now is 3 equations: the red one, the green one, and the purple one. With those 3 equations and only 3 variables, I1, I2, and I3, you should be able to solve. Now, yes, you could do some fancy algebra, you could do some substitution and elimination and whatever else you want to here, or you can just rearrange it so that you have I1, I2, I3, and you can put it into your calculator. So what I recommend is rearranging it so that you have all the variables on one side and all the numbers on the other. So this will be I1 plus I2, and I'm going to subtract the I3 to the other side so that it's equal to 0. I'm going to do the same thing with this green one down here. So I'm going to leave the negative I1 there. That's the negative 1 I1. I don't have an I2 there, but I do have a minus 2 I3. And then I'm going to take that positive 6 and I'm going to subtract it to the other side to give me a minus 6. All right. And then I'm going to use my purple here. And again, I'm going to put together the 6 and the minus 9. And I'm going to move those guys over to the other side of the equation. So in this case, I'm still going to have that negative 1 I1. I've got that plus 3 I2. There's no I3 there. And then when I do the 6 and the negative 9, that'll give me a negative 3, which I then add to the other side, giving me a total of 3. And so now I have 3 equations, which are all in kind of our standard form there, the I1, I2, I3. And you should be able to put this into your calculator for a system of equations now. You have 3 variables and 3 unknowns. Hopefully you should be able to plug that into your calculator and get an answer for I1, I2, and I3. And this is what I get. I1 equals 1.09 amps, I2 equals 1.36 amps, and I3 equals 2.45 amps. And you'll notice that, as we said before, these two guys should add up to give me that one. And if you went through any of the loops, you would find that these currents will work. Now, I did get positive values for all of them, which just means that I chose the right directions earlier. And it's very possible that I made a mistake, and if I did, then I would end up getting negatives here. But the fact that I got all positives means that I chose the right directions, and that's a pretty good place to be in. All right, so from that, we now have all the individual currents. You could now use this to find individual potential differences lost, and any other information that you'd like to get about the circuit. Okay, so that's our introduction to Kirchhoff's laws. I'd like for you to watch one more example of one that's a little bit more complex. All right, go for it.